Okay, folks, let's get started. Today we're talking about motion along a line, and otherwise known as rectilinear motion, right? So for those of you that are physics folks, you will appreciate what we're talking about today. Okay? Particularly if you're a kinematics fan. Okay, so we're going to use S of t. So it's function notation, and we, for whatever reason, we use S to denote a position function. Okay? In physics, you probably use D for distance or displacement, and we're using S of t for position. And so we're going along the S-axis. And so I've got here a graph of, let's say it's a bug, S versus t, so position versus time graph. Tell me what is going on with this bug as far as the motion goes. So let's say that this is the 3 meter mark. We'll say this is, or let's say centimeters since it's a bug. And we'll say time is in seconds. So what's happening right here for this bug? It's moving down, okay, so moving back towards the origin, wherever that is. Can we say anything else about the motion?
Concave down.
Okay, so the graph itself is concave down. So what does that tell me about the motion of the bug?
Accelerating downwards.
It's accelerating downwards, okay. And how do we know it's accelerating?
The slope is going increasing downwards.
Right, we've got negative slope all the way along here, and it starts off here with a very low slope, and then the slope is increasing. So we're seeing an increasing slope. So it's an acceleration, but it's an acceleration that's causing it to move in a backwards direction or back towards the origin. And then here it keeps on doing that. What's happening right here? Yeah, it's decelerating right here, but what about right at this point here? What's happening with that bug? It's stopped, right? It's stopped right there. So the slope of that position time graph is 0, and slope of a position time graph tells me about velocity, right? And then what happens over here? What's happening right here? Nobody knows? It's going back to the reference point. So now is it moving forwards or backwards right here? Okay, so here it's in a negative position, but it's moving back towards the 0. So it's moving forwards. And what about its speed? What's happening with its speed? It's positive speed, and it's increasing till it gets to about here. Then it's fairly steady for a bit. Gets to back to where it started, and then, or not back where it started, but back to the origin. And then what's happening right here? It's stopped. Right? It slows to a stop, and now it's stopped for a while. Okay? So all the way along here, what does the slope of this graph tell me?
Velocity.
Velocity. And how do we find slope of a graph? Yeah, well, on a graph we would take the tangent, but if we had the function, we would take the derivative. So the derivative of the position time graph is the velocity. And so that's what we're talking about here. So the slope is the velocity is the derivative of the position function. So we can write that S prime of t, so the derivative of the position function is the velocity function. And we could also write that as ds by dt, the derivative of the position with respect to time. Okay? Now all of that tells me about instantaneous velocity. So the velocity at any point is the tangent at any point. If we want speed, what's the difference between speed and velocity? Velocity has direction and speed doesn't, right? So for speed, we don't care about direction. Now we're doing motion along a line, so all of our motion is going to be straight line, forwards and backwards, or up and down. We're not going to have any corners or turns or anything like that. So for us, our velocities are all going to either be positive or negative. There's no in-betweens. You're not going to have to worry about any other vectors besides positive or negative. So if we want speed, we're just going to ignore the positive or negative, so we'll take the absolute value of the velocity, and that'll give us speed. So the absolute value of the velocity function, or the absolute value here, is the absolute value of the derivative of the position with respect to time. Everyone okay with that? How many of you have never taken any physics? Okay, so everybody has some physics to refer back to. All right, well that makes this a lot easier. Average velocity, you remember average velocity is change in position over change in time, or back in physics days you probably said total displacement over total time, right? So for us, if we're talking about average velocity, we're just saying the slope of the line between those 2 points. And so the secant is what we call that line. You probably haven't used that word before, the secant line. Secant just means a straight line that joins 2 points on a curve, okay? As opposed to a tangent line only touches the curve in one position. I mean, it can touch in more than one spot, but it's tangent at one point, okay? Questions so far? So we're talking about tangents, which is velocity, and we're talking about secants, which are average velocity. Okay. All right, so here is a function for position of some object with respect to time. S of t is t cubed minus 6t squared plus 9t. Okay? We're going to graph the position function, and we're going to graph the velocity function on here. Okay? So what is this position function going to look like? What do we know about it as far as the graph goes? We know some things about it without really having to do too much, to put too much thought into it. What do we know? It's increasing, right? It's positive cubic, so we know it's going to be increasing in general, so moving up as we go from left to right here on the function. What else? Do we know any points on this graph? Yeah, John? It'll be 0 at 0. I already have the point here nicely, but we know that because if I put 0 in for t, I'm going to get 0 out for t. Okay? Is there anything else that I know just by looking at it? If I factor out the t, I get t squared minus 6t plus 9. Does that factor any further? Okay, so I can see I have another 0 at 3. Okay, and since it's increasing, I know that it must come down and kiss the axis there and go up like so. Okay, because it's a double 0 at t equals 3. And so I have that situation there. And that's what that graph's going to look like. Okay, so we don't have to put any, that's like really grade 11 stuff. Even though it's a cubic, it's like grade 11, grade 12. It's an easy grade 12 question, right? All right, so that's what that function looks like. Now, what about the velocity function? How would we figure out what the velocity function is here? Take the derivative. So the velocity function is going to be the derivative of the position function. So that is 3t squared minus 12t plus 9. And that factors to be 3t squared minus 4t plus 3. And does that factor any further? T minus 3, t minus 1, I think. Right? So what is the velocity at time at 2 seconds? What's the velocity going to be? How will we figure that out? Plug 2 in. So I just want to know what's v of 2. So if I put 2 in here, or even in here, 2 minus 3 is negative 1. 2 minus 1 is positive 1. So I have 3 times negative 1 times positive 1. So the velocity at 2 seconds is negative 3. Whatever the units are, right? Units per second. So 2 seconds is right about in here. And so that makes sense, right? That the slope in there is negative. We've got a negative slope in here. And that's what we're saying. We've got a negative slope, so we're moving in the backwards direction. So if I were to graph this function down here, I have zeros at 3 and at 1. And what kind of a shape is this? It's a parabola, and it opens up. So it looks like so, right? And are there any other points that I can figure out? What's the velocity at time equals 0? If time equals 0, velocity is 9. So it's starting off with a velocity of 9 meters per second. So if I were to extend this, I should be crossing the axis up here somewhere at 9. Okay? And, you know, that's a nice straight kind of curve. Not very well drawn, but... and so 2 seconds is right about here, let's say. And in 2 seconds, you can see I have negative velocity because I'm down below the x-axis. Okay? And at 3 seconds, what's my velocity at 3 seconds? 0. And does that make sense? If I compare it to this, the velocity there, the slope there should be 0. And so the slope, and so here the velocity is 0. Okay? And here now my velocity is increasing. Here my slope is increasing. So the slopes here should compare to the y values here. Okay? Everyone okay with that? So what's the velocity doing after 4 seconds? What's going on with the velocity after 4 seconds? Sorry, pardon me? Yeah, the velocity is increasing, right? So we have, after 4 seconds, it is increasing. And what I'm really asking you is at 4 seconds. What is the velocity at 4 seconds? So we just put 4 in here. 4 minus 3 is 1. 4 minus 1 is 3. So I have 3 times 1 times 3. And I have 9 meters per second, or 9 units per second, because I didn't put any units in here. Okay? So up here at 4 seconds, it's again at 9. Okay? And that should make sense anyways because of symmetry, right? So at 1 second it was at 0, and at 0 seconds it's 9. So at 3 seconds it's 0, at 4 seconds it's going to be 9. It's going to be symmetric on either side, right, Sandrine? Good. Okay. When is the particle at rest? When is the particle at rest? At 1 second and at 3 seconds, right. This is where the velocity equals 0. That's where the function's going to be at rest. Okay? Now if we look at my graph here, 3 seconds is here. Where's 1 second on my graph? Right there, 1 second. Okay, not drawn very well to scale, but that should be 1 second right there. Okay? When is the particle moving forward? When is the particle moving forward? John? Yeah, so between 0 and 1 it's moving forward. And we see that here because we have positive velocity here, and here we see it because we have positive slope. And then from 3 seconds on we have positive velocity here and we have positive slope here. So it's moving forward from 0 to 3, and, or sorry, 0 to 1, and 1 and 3 to infinity. How about this question? What is the displacement for the first 5 seconds? How are we going to find the displacement of this function, of this bug, for 5 seconds? The y value of the first graph at 5 seconds. So figuring out where that is. Okay? And how else could I figure it out? From the graph, or, yeah, put t equals 5 into this function here. So 5 minus 3 is 2. So I have 5 times 2 times 2, so that's 20. Okay? Questions for me? So it's all, this is applications of the derivative. So the derivative here is telling me the velocity function, and then we're just answering the questions and using the correct graph or the correct function. Find the average velocity for the first 5 seconds. So remember, average velocity is total displacement over total time. What's the total displacement for the first 5 seconds? 20. The time is 5 seconds, so we have 4 units per second is the average velocity. Okay? Questions about that? Okay, what if we wanted to graph speed versus time? What would that look like? Okay, right, so here's my velocity time. Or that's 9 seconds, that's 1 second, and that's 3 seconds. What does the speed time look like? What does it mean to take the absolute value of this? Right, we're going to have that W shape going on. Okay? So that's what the speed time graph is going to look like. So notice there the speed is positive everywhere because we're not interested in the negatives. Okay? Now, acceleration, you learned in physics, is the rate of change of velocity. So how do we find acceleration? Second derivative of the position function or first derivative of the velocity function. Good. Okay? So acceleration is the first derivative of the velocity function or the second derivative of the position function. Now, so here's something to think about here. Here's one of your physics formulas. What is this formula from? Yeah, it's from physics, but what is it telling us? It's the displacement of an object. Yeah, and this particular object must have constant acceleration, right? So if we have an object with constant acceleration, this will tell me the displacement of the object, okay? Right? So the first derivative here, how do I take the first derivative? What's the thing that's changing here? What's the variable in all this? T. So if I take the first derivative of that, I get V naught. And if I take the first derivative of this, I'm going to go 2 times a half is 1 AT. Okay? So that's our velocity, right? Remember that formula? So that's the velocity of an object with initial velocity plus AT, right? Now let's take the second derivative. Second derivative obviously is just A. Right? So those formulas don't come from, they're not just made up. They work. And the derivatives get us back to where we need to get back to. Okay? All right. Now, how many of you are going to be taking physics next year? How many of you are taking a higher level of physics next year? Like if you're going into engineering or something like that. Okay? So when you get into your higher level of physics, you aren't going to be doing this kind of Joe stuff. You're going to be doing everything in terms of calculus. Okay? And so next week we're going to look at related rates, which is really what your physics course is going to look like. It'll be calculus-based physics. Okay? And even if you're taking a Joe physics next year, the following course will be calculus-based. Okay? For those of you that just had physics 11, you probably won't jump right into calculus-based physics right away. All right. A dynamic blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of S equals 160t minus 16t squared after t seconds. Okay. Does this formula look familiar to you? It's the same as this one here, right? What's the V naught? 160 feet per second. What's the acceleration? 32 feet per second squared. Okay? Yeah, 9.8 meters per second squared is acceleration due to gravity, but it's 32 feet per second squared. Okay? Because we're in feet. So that's where that's coming from. It's not. I'm not making this up. Okay? This is a real value here. You just never worked with feet in physics before, possibly. Okay. So how high does the rock go? It goes very high, but I'm asking you to find the maximum height of this rock. It's a heavy rock. Take the derivative. What's the derivative going to tell me? It's going to tell me slope. And what kind of slope am I looking for at the height of this rock? Zero slope. Good. Okay, because at the height, at the top of this, when the rock goes up at the top, the velocity is going to be 0. So I'm going to find the velocity by taking the first derivative. Right? I'm going to set that equal to 0. So where is 160 equal to 32t?
3tt?
Oh, 32. I wanted to write. Okay? So I need 160 divided by 32. What is that? To 5?
6.
So 5 seconds. Okay? Everybody okay with that? Yes? Okay? All right. That is how long it takes to get there, but that's not the actual height. How am I going to find that height? Plug this back in here, right? So S equals 160 times 5 minus 16 times 25. What does that work out to be? Come on, Kenny.
Okay.
Anybody?
48.
No. Somebody with a calculator. You're all sitting here with calculators. What have we got?
350 maybe?
Sandrine's using her phone. 400. No?
That's 16 times.
That's 16 times 25 is 400?
Yeah.
Okay.
So everything's 400. So it's 800 minus 400.
It's 800 minus 400. Good. Close? All right. So the maximum height is 400 feet. So now the question is, at what time is the rock 256 feet in the air? Make what equal to 256? Right, so we want to put our position is 256. And to solve that for t, what are we going to do?
Divide by 16.
Divide by 16. Okay, so I have t squared minus 10t plus, what's 256 divided by 16?
I don't even know if it works. I'm just guessing.
60?
16.
16? All right, so we got t minus 2, t minus 8. So at t equals 2 or t equals 8. Why 2 different times? Because it comes back down. So on the way up, at 2 seconds, it's going to hit 256 feet. And on the way back down, at 8 seconds, it's going to hit 256 feet. So at what point is it going to hit the ground?
That's moving. That's fast.
When the displacement equals 0, what time is that going to be?
0 first.
Yeah, so when does it hit the ground? After it's gone up in the air. We're talking symmetry here. Has to be 10 seconds, okay? And you can tell from a couple of different ways. Halfway is the 5-second mark, right? That's when it hits the maximum height. So it takes another 5 seconds to come back down, so that's 10 seconds total. Or it takes 2 seconds to get to 256. That's 2 seconds away from 0. Then on the way back down, it's 2 seconds away from 0 again. So at 10 seconds, it's going to hit the ground. What are we ignoring in all of these? Air resistance, right? So things aren't going to be exactly like that, but that's what we're looking at. All right, how do we find the acceleration of this function? What are we going to do?
Negative 9.8 meters per second squared.
What do we do to find the derivative of, the acceleration of this function? Second derivative of the position function, or the first derivative of the velocity function. So the velocity function was 160 minus 32t, so the acceleration is going to be minus 32 feet per second squared, which we talked about at the very beginning. And when does the rock hit the ground? We said at 10 seconds. Questions about that? Yeah, John.
Can we never use real values again?
Oh yeah, you can. Just in this problem we didn't.
Please, no. Just hear me.
Well, too bad. I mean, one of the reasons we're using them is so that you don't just jump automatically to the 9.8, so that you actually do a little bit of thinking about it. But all right, let's think about the graph here of this rock, the position function. So it hits a maximum of 400. Let me make these a little bigger because I can. So at 5 seconds, it's hitting its maximum and is starting at 0 and coming back down to 10. So there's the position function graph. Okay. What does the velocity function look like? Just go back and look at the equation.
It'll start off at its highest and then go down.
It'll start off at its highest and go down. So what is its highest?
Its highest is at point which is 0, so
What's the velocity at time equals 0? That's what I'm asking you.
it's 160.
160. And what shape is this when I graph it? It's a straight line, right? With what kind of slope? Negative slope. Good. So this function is going to start at 160, and at 5 seconds it's going to be at 0, and then at 10 seconds it's going to be back to negative 160. Notice that I didn't draw that really beautifully. Let's see if I can draw it a little bit straighter. So it's going to look like that. That's what my velocity function is going to look like. What's the acceleration function going to look like? Straight line. Same as like velocity? Horizontal line right here at negative 32, like so. Everybody okay with that?
Yeah.
Okay, so let's talk about acceleration, because we use acceleration in physics to mean speeding up or slowing down. But if you think about it, the object's only going to speed up if the acceleration and the velocity have the same sign. So if you're moving forward and your acceleration is forward, then your object's going to speed up. Or if you're moving backwards and your acceleration is backwards as well, then your object's going to speed up in the backwards direction. But if they have opposite signs, then they're going to work against each other and you're going to have slowing down. Right, Kenny? Mm-hmm. Right, Kenny's friend? Put Kenny's friend away. There we go.
He's right. Yeah.
Okay. So these things should also make sense to you because you've all studied physics. If the position function is positive, that means we are on the positive side of the t-axis, okay? We're above the horizontal axis. If the position function is negative, then we're below the horizontal axis. Right, Jack? Wake up, Jack. Wake up, Jack. Okay? The slope of the position function, or the position time graph, is the velocity. So if the velocity is positive, then the object is moving forwards. If the velocity is negative, then the object is moving backwards. If the velocity is 0, what's the object doing if the velocity is 0? Yeah. What is the object doing if the velocity is 0? It's not moving, or we say it's stationary. Okay? If the acceleration is positive, that tells me that your position time graph is going to be concave up. That's your second derivative, right? And a positive second derivative is concave up on the original function. If the acceleration is negative, then the position function is going to be concave down. And if the acceleration is 0, then the velocity will be constant. Right? All review for you, except the concavity piece. That's the new piece. Yeah. All right, so I'm going to do one more example with you in just a moment, and then you're going to get a chance to practice these in your book. And there are a lot of practice problems for rectilinear motion in your textbook, so you're going to get lots of opportunities to practice. How's that, Alex? Can I go to there?
Yeah, true.
All right, give it a minute. Okay, where are you at, Alex? Did I go past it? No, are you sure? I don't want to go past it. Is that okay there? Okay. All right, how about I write it on the board? And then if I'm going to do that,
I want to write on that.
I will